Hello, today we are discussing about binary search tree. So we have already discussed about what is binary tree. Now binary search tree, it is a binary tree itself, but it has certain property. Now because of this property, it is easier for you to search element in the tree, and it is showing a better performance for searching, insertion and deletion. Okay, we will try to know what is the definition of a binary search tree. Now as per the definition, a binary search tree is a binary tree. It may be empty or it is not empty, then it satisfies the following properties. Every element has a key. So here what we are saying is every element, every node has a value, and one more condition is no two elements have the same key. That is the precondition. Every element, every node has a value, and no two elements, that is only single unique value should be there in the node. So no two elements have the same key. That is the precondition for it. Now the keys in the left subtree are smaller than the keys in the root. So all the keys in the left subtrees will be less than the value of the root. And another condition is that the keys in the right side tree always larger than or equal to the root. So left and right subtree are also binary search tree, meaning left subtree also will follow the same property. Similarly, the right subtree also should follow the same property. Now we can check an example. So the first tree, you can see here, it is not a binary search tree. Here it is written. We will check why it is so. So you can see here 20 is the root. As per our definition, all the elements in the left subtree should be less than 20. Okay, that is fine. All the elements is less than 20, and all the right subtree should be greater than 20. That is there. But you can see here, this we can take the left subtree. So if you are taking the left subtree, 15 is the root. So left of 15 should be less than 15. Okay, 14, fine. But you can see that right of 15 is 10. It is supposed to be greater than 15, but here it is 10. So similarly, you can see here right of 20 is 25, that is fine, but this right subtree, the right of 25 should be greater than 25, but here it is less than 25. So because of these two conditions, it is not satisfying the property of binary search tree. At the same time, we can check the second example. You can see here it is a binary search tree. Why? Because 30 is the root, and whatever the left subtree, it is less than 30, and whatever the right is greater. Now if you are checking the left subtree, 5 is the parent, then left of it is less than it, and here it is following it properly. So I can say it is a binary search tree. Now take this tree. In this, the root is 60 and the right of it is 70, and 70 left is 65, which is lesser, and right of 70 it is 80. Hence it is a binary search tree. Now as I told already, searching a binary tree is the much easier, and the performance is better here. So we will check how the searching is being done in a binary search tree. Now here assumption is if root is 0, meaning no value is there, then that is the empty tree, no search is assumed. So here the assumption we are taking, root is 0 means no value is there, it is an empty tree and no search is needed. Now if the root is not 0, meaning tree is not empty, what how the comparison is being done. That is what we are discussing here. Suppose assume that X is the element I want to search in the binary search tree. So here it is saying if the root is not 0, compare X, that is the element we are searching for, with the root of the tree. So X I wanted to search and I am comparing it with the root. Now initially if X equal to the key of the root, so what I am searching for is available in the root itself, then it is being done. So search is being done. Otherwise, if the value you are searching for is not in the root, what you have to do is we are checking whether X is, compare the X with the root. If X is less than the key of the root, then no elements in the right subtree can have the value of X. Already we know that binary search tree is following the property like all the elements which is less than will be in the left subtree and greater than of the root will be in the right subtree. Hence, if the element you are searching for is less than the key in the root, no need to go for right side of the tree. The value will be there in the left side. That is what the assumption. So X is less than the key of the root, then no elements in the right subtree can have the key of the value. We can only need to search in the left subtree. Now similarly, if you are searching for is greater than the root, then definitely I can say that the value will not be available in the left subtree, it will be available in the right subtree. So this way we are searching for the element. So we can take an example and try to find out it here itself. So suppose I am searching for 2, take the middle tree. Suppose I am searching for 2, what I will do is I will compare 2 with 30. So we already know that 2 is not equal to 30. What we will do, since it is less than 30, we will come and check it in the left subtree. So we will be checking it with 5. So it is not equal. So again we will come back to the left side of it and here we will get it. So this way we are searching the binary search tree. Now insertion to a binary search tree. So what we have to do is we have to insert a value into the binary search tree. So initially before inserting we had to identify whether the element is in the tree or not. So as per the condition of binary search tree, no two elements have the same key in the binary search tree. So we have to make sure first the element is in the tree or not. If it is not there, then only we have to insert. So initially what we have to do is we have to perform a search first. So before insertion is to be performed, a search must be done to make sure that the value to be inserted is not already in the tree. So if the search fails, we know that elements we are searching or inserting is not in the tree, so we can definitely go and insert it. So if the search fails, then we know that the value is not in the tree, so it can be inserted into the tree. Now it is written as it takes order of height to insert a node into the binary search tree.